let us calculate the equation, or find the equation of the tangent plane and the normal line to this surface. X squared plus 4y squared plus z squared is equal to 12 at the point 2, 1, negative 2. Now, I'm going to ask you to pause the video, write it down, and try it. Okay, you did. Alright. Now, we're going to look at this problem. But we're not going to just work it out like how you would do in an exam. We're going to take our time to discuss the theory behind it. Alright? Now, here, you have a surface. It could be some type of surface looking like this. Alright? And then we have a tangent plane. Plane that touches the surface at some point. Alright? So it touches it here. Now, what we are looking at here is a surface. It's curved, as you see the squared in the x, y, and z, and then a plane. It's flat, it's like a tile or something like that. Alright? Now, how do we find the equation of a plane? Well, if you have a plane, say this is a plane, you have vectors on the plane. You have an infinite number of vectors that you can look at, alright, pointing in all directions. Now, what you do here, the basis of this equation for the plane, comes from the fact that you can have another vector that is said to be orthogonal to this plane. It's at 90 degrees to the plane at every point. Alright? Now, we have this vector being at 90 degrees. It is 90 degrees to any vector that you will put on this plane. What that means is that the dot product is equal to 0. Alright? You remember from vectors that when you find the dot product of two vectors, if they are 90 degrees to each other, the dot product will be equal to 0. Now, let's redraw this plane. This is our plane again. We have a specific point on the plane. Now, that point, let's just put an arrow on it. It is at x0, y0, z0. It's a specific point. You can say it's at ground zero, the point where things are happening. Alright? Well, you have a general point. That general point could be here, it could be here, anywhere. Let's say for a moment we have a general point at x, y, z. Now, the vector that connects these 2 points would be x minus x0. That's the distance there. Alright. It's a vector, so remember, use the these shapes, these type of brackets, to include the vector x minus x0, y minus y0, z minus z0. Alright? It's like saying x minus x0, I plus y minus y0, j plus z minus z0, k, where I is a unit vector in the direction of the x, j is unit vector in the direction of y, z is unit vector in the direction of k. And remember, as I said before, I'm looking at the theory behind this. And when you know the theory behind it, if you have an exam and you're not given a formula sheet, it's easier to remember, or you could quickly derive the formula, right? If you didn't remember what it was. Alright, so here it's like you're saying, if you have the x, y, and z axes, then you have two vectors here. You have a certain direction. In the x, it's above this point, but, well, not exactly above it, but if you have a certain direction on the y, a certain distance in the y direction, and then some other distance in the z direction. Alright, say it's here. I missed the point. Say it is here. Alright? So, in order to locate that point, from here you go x, y, z. You have the x component, the y component, the z component, and it's right here. You could very well just take a vector coming straight here. Alright? So you know that it is this distance in the x direction, this distance in the y direction, and this distance in the z direction. So you locate it right there. Now, here, this other vector that is at 90 degrees to the plane, let's call it the normal vector. Let's call it n. Now, n is a vector with components a, b, c. So that's our vector there. Now we know that the dot product of these two vectors is 0. Alright? So here, what you can see is that the vector x minus x0, y minus y0, z minus z0, dot a, b, c is equal to, and remember how to calculate the dot product, right? You're going to multiply this time this, plus this time this, plus this time this. So it's going to be x minus x0 multiplied by a, let's put the a here, plus the y minus y0 times b, call it y, y minus y0, plus, and then c, z minus z0, right? I'm crossing my z there, is equal to 0. Now that's the equation of a plane. Now, here, in this case, we're looking at gradients. So A, B, and C will be our gradient. Now, do you remember the formula? Something like Z is equal to delta Z by delta X times the change in X. The change in Z is delta Z by delta X times a change in X plus delta Z by delta Y times a change in Y. You remember that? It's somewhat similar. Somewhat similar thing will happen here. A is our gradient. So we say this is, let's say this is f of our vector f is this, delta f by delta x times x minus x 0. Then we have plus b is actually delta f by delta y minus y 0, plus c is really delta f by delta, well, is the wrong delta I'm putting, delta f by delta z times z minus z0 equals 0. Now, this is going to be the equation of a tangent plane, and you notice that this change in x is x minus x0, delta is f by delta x minus x0, and so on and so forth. Alright? So you see that. Now, we're going to need delta f by delta x, delta f by delta y, delta f by delta z. Alright? Now, here, what we need is the gradient of the vector. Gradient of the vector that's associated with the surface. The surface is x squared plus 4x. No, x squared plus 4y squared plus z squared is equal to 12. So we have x squared plus 4y squared plus z squared equal 12. But in order to write it so that it's equal to 0, we have to subtract 12 from both sides. So we have x squared plus 4y squared plus z squared minus 12 equals 0. Alright? Now, the gradient represented by an upside down triangle. I read somewhere that it's in the form of a harp, and historically that was used by mathematicians as the symbol to represent the gradient. Alright? So that's the gradient of our vector f. Right? This, oh, where I wrote it here. Yes, this same vector. Now, this is going to be represented as a vector delta f by delta x, delta f by delta y, delta f by delta z. So that vector there will represent the gradient. Now, what is delta f by delta x? Delta f by delta x is equal to, notice we're going to have 2 times x here, so it's 2x. We are treating y as a constant, so this will be 0. So it's 2x plus 0 plus z is a constant, which is 0, because we're differentiating partially with respect to x, plus 0. Negative 12 is a constant, alright? So it's the partial derivative of x with respect to x. What is the partial derivative of f with respect to y? Well, here, x squared will go to 0, right? Because we're treating x as if it is a constant for the time being. For the 4y part, 2 4 is 8, so this is 8y. Then z squared will be 0, because z is a constant for now. Negative 12, of course, 0. Then we find the partial derivative of f with respect to z. Well, the x squared X is being treated as a constant, so is y. So these two will be 0. Then we have 2z, and then negative 12 is 0. Alright? So that means the gradient of f, the gradient of the vector f is 2x, 8y, 2z. So you see that. Now, here, what happens at the point that we were given? What was the point again? The specific point was 2, 1, negative 2. Alright, so let's go back there. At 2, 1, negative 2, the gradient of f is equal to 2 times 1, no, 2 times 2, x is 2. So we're going to have 2x, this is x, 2 times x, 2 is 4, comma, 8 times 1 is 8, 2 times negative 2 is negative 4. Alright, so that's our gradient as f. Now, let's look back at our equation of the tangent plane. Delta f by delta x times x minus x naught, x0, alright? Now, the thing is, what is it that we call x0? Well, it is actually the value of x that we're given here. This is x0, this is y0, and this is z0. The coordinates of the specific point, that's ground 0 right there. Alright? Now, let's rewrite the equation for the tangent plane. Delta f by delta x, x minus x0, plus delta f by delta y times y minus y0, plus delta f by delta z times z minus z0 is equal to 0. Now, delta f, and by the way, these things occur at 2, 1, negative 2, alright? All of them occur at that point. Alright? Now, here, delta f by delta x at that point, we already calculated it, you know. Delta f by delta x generally is 2x. But at 2, 1, negative 2 is 4. So what we have is the delta f by delta x at that point is 4 times x minus x naught is what? x0. Oh, right here. So here we have our x0, y0, z0 is x minus 2. You see that? Plus, here we have delta f by delta y at this point 2, 1, negative 2. It had turned out, remember, delta f by delta y was 8y. And at 2, 1, negative 2, y0 was 1, so it's 8 times 1. So it's 8. It's 8 times x, not x. Y minus, what was y0? It is 1. Plus. And then delta f by delta z was 2z. And when we put in 2, negative 2 for z, we get negative 4. So actually going to be a minus 4 times z minus, and z0 is negative 2, but minus negative 2 means plus 2 equals 0. So you see that. Now here you can expand the bracket and simplify. This would be 4 times x, 4x minus 4 2s 8, plus 8y minus 8 1s 8, minus 4z minus 4 2s 8 equals 0. So we have 4x plus 8y minus 4z, negative 8 minus 8 is minus 24 equals 0. So seems like we run out of scrolling space. Now this implies that 4x plus 8y minus 4z is equal to 24. And you could divide by 2, and you have 2x plus 4y minus 2z is equal to 12. So that's a formula for the tangent plane. Now let's look at the formula for the normal line. Now for the normal lines, you're going to introduce that, well, we have x, y, and z already. A fourth variable, which you call a parametric variable, which is t. Alright? Now, you will generally see that the equation for the normal line is x is going to be equal to, it's going to be the point. You usually see it as x0 plus t delta, delta not x, it's delta f by delta x. But let's rewrite it in this way. Let's put the t part first. It's delta f by delta x times t plus x0. You have y is equal to delta f by delta y times t plus y0, and z is equal to delta f by delta z times t plus z0. Why I put it this way is that it's easy to remember that the general equation of a straight line is y is equal to mx plus c. M is the gradient, and when you differentiate, you find in the gradient function. So you have the gradient part here, you have the variable t, and then the constant where you have an intersection here is z0. You probably want to remember it like this. Now here we want to look at substituting the values into these equations to find the equation of the normal line. Now delta f by delta x times t, delta f by delta x at the given point is 4. So it's 4, 8 and negative 4 that we have. So x is equal to 4t plus, what was x0 again? Was 2. Then y is equal to, so we had 4, we had 8. So 8t plus, and then the second point was 1, so it's plus 1, and z is equal to, and we have what was it, negative 2, negative 2 My memory served me right. No, negative 4. So it was a negative 4 t plus, and that point, specific point, was negative 2. Well, it will turn out to be minus 2. Alright, so these are the parametric equations for the normal line. Now you could very well transpose each for t. If you transpose each of them for t, in this case t is equal to x minus 2 divided by 4. In this case t is equal to minus 1 divided by 8. And in this case t is equal to z plus 2 divided by negative 4. But all of these are t's and are the same. So you could have x minus 2 divided by 4 is equal to y minus 1 divided by 8, and that is equal to z plus 2 divided by negative 4. And then of course you could multiply everything. Suppose you multiply everything by 8, what would happen? 4 into 8 goes 2 times. You'd have 2x minus 2 equals y minus 1 is equal to, if you multiply this by 8, you'd have negative 2 times z plus 2. Alright, so that's what you'd have there. Alright, so if you should multiply out the brackets, you have 2x minus 4 equals y minus 1 equals negative 2z minus 4. Okay, so there you have the equation of the normal line.